Alright, so vector and scalar quantities. So those of you who enjoy physics, you should have an idea of this. So scalar. Scalar would refer to something like distance, while vector would refer to something like displacement. So the difference between the two is a scalar measures a quantity that has size only. Okay, so when we talk about size only, we don't care about direction. That's all we care about. Like, wherever you gotta go, if you went 10 meters, you went 10 meters. If you drive for 15 miles, you drive for 15 miles. I don't care if you went east, north, south, west. I don't care. The only thing we care about is the actual quantity. So that's what we refer to as scalar. So an example of this would be distance. So as you can see here, this person maybe was walking all this way, went this way, come down here, and went this way. So this covers the distance that they travel. The purple line shows the distance that they travel. So now a vector now would say we care about the quantity and we care about the direction. Okay, we care about the direction. So an example of that would be, in this case, displacement. So if I'm traveling somewhere, I could be traveling 30 miles per hour due east. Okay, so in this case now, looking at this displacement here, if this is north, here's east, I would roughly say here could be southeast, right? So if this is southeast or whatever the case is, my displacement really was from here to this point here. So essentially that means that if you started walking from this point, so here's where we started to walk. Make sure you're looking at this, huh? We start to walk right here. We ended up here. That's your displacement. You moved from this point to that point. Whereas distance now, you travel all the way around here to get to this point. But in terms of displacement, you really and truly move from here to over here. Okay, so it's a little odd concept, but essentially when we talk about displacement of vectors, we're just talking about, you know, the change something had relative to where it was, as opposed to everywhere it traveled. We're looking at it from a straight point of view, like you travel in one straight line. So if there's a path to get to your house from school, this is like you walk straight to your house, even if you're running through the bush, everything. Y'all follow that? So when we talk about vectors now, we usually have a journey from one point to the next point. So in this case here, we got a journey from O going to B. Now if we're talking about a journey from O to B, we can refer to that as OB. So OB with this fancy arrow at the top. So this fancy arrow at the top is what calls it, what denotes it as the vector. So here is OB. So I'm going from O and I'm ending at B. I have this arrow at the top. Now if I'm going the opposite direction, so I'm going from B to O, I'm going to call that BO and put the same arrow at the top. Does that make sense? So if I'm going from Stony Ground to North Hill, it's like you put them next to each other. Stony Ground, North Hill, and at the top of it, you would put the arrow. Okay, so the arrow shows where we are going from O to B. In this case, we're going from B to O, so we say BO. Usually when we represent vectors, we either use letters or column vectors. You either use letters or column vectors. That's going to be very important. So the column vectors would be the ones that we're going to look at today, and we're going to look at the ones with letters another time. So the ones with letters is kind of like, think of it like algebra in a sense, right? So when we get to that point, you're all going to see what we mean by that. Everybody got that down? So what I would put here too is a little diagram so you could see that it's one displacement from O to B. All right, so we finished now? Okay, so a position vector gives the position of a point relative to the origin. So y'all know what the origin is. Right here is the origin. Origin is this point right here. Everybody knows what that is. So a position vector is written in the form of a column vector as seen below. So as you can see here, x, y is one way that we write it. This is another way that is written, but y'all won't see it for your level, but just in case, it's literally the same thing as writing it like this. Okay, so this is our most important one right here, and I guess you can figure out what XY means, right? That's almost like the X movements versus the Y movements. So you'll see how we do position vectors in a bit, but remember, in order to be considered a position vector, it must come from the origin. That's the most important thing. Must comes from the origin. And usually when it comes from the origin, we use a letter to let us know. What letter do you think we would use to come from the origin? Oh, good. If you have a vector called O to S, more than likely that is a position vector. Why? Because it's coming from the origin. Make sure y'all writing this down so you don't miss anything, especially the fellas. You'll be checking out your books. Don't play no games. Alright, let's go to the next slide. So when you look at this here now, direction of a vector, we're going to just give you an idea of what's going on. So A is what we know as a coordinate. So just 6, 8. So we are 6 on the x-axis and 8 on the y-axis. That's what we refer to here as a coordinate of A. Now, to turn this to a position vector, it must come from the what? Origin. Good. So then our movements would be from O to A because we're trying to get from O to A. All right. So if we're trying to get from O to A, we have to go 6 to the right and then 8 up. Okay. 6 to the right and 8 up. So then we got from here now OB. So this is OA, sorry. So this here is our vector OA. And my arrow here is showing me the direction that I travel from O to A. So 6 right, 8 up. Now to write as a column vector, this is how I'm going to do it. So this here goes up and down. That's why we call it a column. Just like you have columns in your house, that's why we have it called as a column. So a column vector goes up and down. So 6, 8, our vector O to A. So O to A is a position vector because it's coming from the origin O. Does that make sense? Yeah. So this here is just for y'all to, you don't have to necessarily write this down, right? This is just to show you visually what the vectors that we're talking about are. So we were talking about position vectors. This is basically showing you how it works. Once you're moving from right, you go positive. Once you go up, you're also positive. Okay, let's look at the next one. So with this one, this is B. B is a 0.6, negative 8, right? So how do you think we can make a vector from O to B? We have to go O to B to get that position vector. So we have to go how much to the right to get to B? 6, and then how much down? 8. So we go down 8. So now this is where the direction part comes in, right? So we essentially going down 8, which is why we refer to it as negative 8, because going down 8 means you're negative. If you were going up like the last time, it would be positive. Okay, so up is positive, down is negative. Just like these number lines, going up is like positive, going down is negative. If you go right, it's positive numbers. If you go left, it's what kind of numbers? Negative. Okay, does that make sense? Makes sense, right? How would I write this as a position vector? If I'm writing this as a position vector O to B, what would I write? How? 6 at the top, negative 8 at the bottom. And then if I'm writing it in vector form, like the letters together, how will I write the letters? The letters, not the numbers. Try again. OB with an arrow. Don't forget, OB with an arrow. So this indicates that it's a vector O to B. You following me? And that's what we have here, 6, negative 8. Okay, so we write these as column vectors, but the name itself is considered O to B. Okay, so we'll try 2 more like this again so y'all could see the concept. So this concept now, we have C. So if I want to get a position vector, I must go from where? Where am I starting? The origin. So what am I going to end up calling this vector? We'll see. And how I'm going to know it's a vector? The arrow on top. Right. Now, if I'm reading from here to here, I have to go how much to the left? 6. So because I'm going to the left, that's why I call it negative. And then when I'm going up, I'm going to do 8. Okay, so then I would have negative 6, 8 as my column vector. Does that make sense? Straightforward, right? Okay, nothing hard so far. Now this one here, what do you think this one is going to be? From O to D. O to D is going to be written as what? Yes, OD with a arrow at top, then what? Good. Remember, we always treat it like XY, the same story. The X movements first, then the Y. Okay, so then we write it like this. Does that make sense how we write these vectors? So we got equal vectors. Vectors are considered to be equal when they have the same magnitude of size and direction. So if you have the same size, that's one thing, but you can't have different direction. Otherwise, it's not equal. It has to be the same size, has to be the same direction. So if you look at these 2 vectors here, they're going in the same direction. So A is the same as B. They're equal. They have the same size and they have the same direction. Okay, so that's what makes a vector equal. So this is a theoretical concept that CSEC expects you to know. Just knowing theoretically that if anything is equal, that means that they must have the same size and direction. I want you to take this down. All right, so geometric relationships between vectors. So just how we say they are equal, we want to talk about what characteristics can we compare. So the first one we're going to talk about is size. So when we're talking about size, it could be the same size, twice the size in opposite in direction, those kind of stuff. So if you look at something, you can say, oh yeah, that's 3 times bigger than that one. Or you say, oh yeah, that's like 4 times bigger than that one. That's 2 times bigger than that one. That's 1.5 times that other one. So when we talk about geometric relationships, the first thing we want to look at is the size. All right, the size. And just a heads up, when we're calculating the size of a vector, we're going to use our good friend from trigonometry, Pythagoras theorem. Yes, we will be using that again. Now the next thing we would look at is whether they're parallel or not. So size is our first one and parallel is the next one. So parallel lines, what do we know about parallel lines? They don't meet at any point in time. Why don't they meet at any point in time? Because they have an equal distance away from each other. Now I have a question. What if they were actually on the same line and touching? Would that make them, would they be parallel? Why not? Right, so because of that, we have something else to call that, which is collinear. Okay, so we call it collinear. So when some lines are considered to be collinear, it's the same line, it's basically like the same line, but they share a common point. Okay, they share a common point. So for instance, if you look at these here, when we talk about the first geometric relationship, which is size, we are saying that, red is compared to like blue here. If we compare them in terms of size, what would you say? Someone tell me, what would you say in terms of size? Who is 2 times the size? Blue is 2 times the size of red. Excellent. What about blue versus green? Same size. Parallel. And they're parallel, right? So that's two geometric relationships you just talked about. One, the size. One that is parallel as well too. That's the second one. Okay? So the size, they're the same, blue and green, and they are also parallel. Now let's talk about collinear. So collinear now, if I'm looking at A and B, and then I'm looking at B and C, what's a common point between AB and BC? B. So B is a common point that they share. So I'm going to say, these guys can't be parallel because they are touching. So if these are touching, I have to refer to them as what? Collinear, right? Good. So imagine parallel. Imagine the lines are like parallel in the sense of they're going in the same direction. But instead of just going in the same direction, they're actually sharing a point. So because they share a point, that's why we say they're collinear. Okay? So you can't say something is collinear if one line going this way and the next one bend that way, right? It has to be a case where they're going in the same direction, but they share a common point. Does that make sense? So these are going to be your 3 crucial geometric relationships with vectors. So if a question asks you, what is your geometric relationship between this and that? The first thing you got to look at is, what's the size difference? Is it one twice the size as the other one, blah, blah, blah. Then you got to look at, okay, are they parallel? Are they not parallel? But you also need to know if they're collinear, because they cannot be collinear and parallel at the same time. Does that make sense? Good. All right, so take this down and then we continue going. You guys understanding the concept so far, right? Concept-wise, like theoretically speaking, it making sense, right? Mathematically. So this part of vectors is a nice part. The numbers part of it. The letters is where it starts to get a little trickier, but we need to make sure we understand this part of it first. Once we got this part, on the exam, it's either one that comes. You apply the same concept that we just spoke about for both, but there's one that focuses on numbers and the other that focuses on letters, right? And we'll explain and understand the difference between the two, because essentially they're the same thing, but they're still different. These topics here, don't be afraid to put on your diagrams. I would always recommend to put on some kind of diagram to show what it looks like visually, because it helps a lot when you have to answer questions that don't have diagrams. All right, so let's look at the next one now. So, scalar multiplier. So when we're talking about a scalar multiplier, this is a number multiplied by a vector which could increase its size, decrease its size, and or change its direction. I'm going to throw a wild card out there, right? But before I throw that wild card out there, let's try it small first. If I want to double a vector, what number you think I'll multiply it by? By 2. If I want to triple it, what do you think I'm going to multiply it by? Okay, good. What if I want to double it and then change the direction? What do you think I'm going to multiply by? -2. Excellent. The negative is what's going to help us to change the direction. Okay? So, when we talk about that, that's going to kind of help us to figure out whether something is parallel or whether they are collinear. Okay? So, two vectors are parallel when they have the same scalar multiples of each other. And we also have to have different letters. Okay? So, they can't share a letter. They can't share a letter. If they're sharing a letter, that means they're what? Collinear. Good. So for instance, let's call two random vectors. So from O to B, I have a vector O to B and a vector C to G. OB, CG. Two different vectors. Do they share a common point? No, they do not share a common point. Let's try the next one. M and T is one vector, and the next vector is T and Z. So I have MT and T and Z. Do they share a point? They share a point. Good. So in this case, I did not say that they are collinear or parallel because we need to make sure they have the same scalar multipliers. However, all I wanted you to be able to identify is that whether they share a common point or not. Okay? Alright, so you guys should have this one by now. So collinear. So parallel vectors which lie along the same line are considered to be collinear. So technically they are they kinda could deceive you and make you think they're parallel because they're gonna be scalar multiples of each other. However, when they share a common point is what makes them collinear. Okay? So this goes back to this here. So if we had to use this as an example, we could either say A to C. Let's just say we had this one line A to C, and then the next one we had was A to B. A to B, A to C, and they are scalar multiples of each other. Do they share a common point? A, B, and AC. Do they share a common point? What's a common point? B. Right. You sure? 100%. You heard what I said though, right? A to C, then A to B. What's the common point? A. In terms of the name that I'm giving you. Now, if I say A to B, then B to C, then you have a common point, which is B, right? Yes. Good. All right. All right. So basically, that's the difference between the two. That was just giving you a little breakdown just to clarify in case you missed it earlier. So in terms of magnitude, when we're talking about the magnitude of a vector, we're talking about the size. Okay. So we're going to treat it like a triangle. We're going to treat it like a triangle. So this triangle would allow us to use Pythagoras theorem. Okay? And then if we have a vector that has a size of 1 and not 1.02 or 1.05, 1, we call that a unit vector. A unit vector. So another way of writing a magnitude of a vector, if they're trying to get you to figure out what the magnitude of a vector is, they will ask you like this. They can ask you just like this. Okay? They put the lines there just like how they do that in matrices. What do they use this in matrices to X? Ah, the determinant. Tell the people them, the determinant. And inside of vectors, we use that to find the magnitude. Okay, so that's very important. So I want you guys to take this down. This is here basically Pythagoras theorem. So we'll see how that is done as well. So essentially this is what it looks like, when we go from left to right or whatever, then up or down, and then we form the vector. So that's basically how it looks like a triangle. Okay, so let's look at this question here now. So the first thing we want to talk about is writing OA as a column vector. Now, the long way of doing these things to figure out what it is, we can count each space, right? So say for instance, I'm going from O to A. So that's what we are looking at, O to A. Okay, so O to A, I'm starting from where? Where am I starting from? What's this called? Origin. So I'm going 1 to the right, 1, 2, 3, 4, 5, 6, 7, 8. So O to A is equal to, writing this as a column vector, I have to put up here 8, right? And then to go up now, so now I have to go up how much? 1, 2, 3, 4, 5, 6. So then I could write it as 6. So 8, 6. Does that make sense? So I want you all to write that down as well as a question. So you all followed how I did that, right? Okay, so let's get rid of that. So let's put OA as. Now, the next question is AO. So what are we doing here? We're doing the opposite. We're doing the opposite. So how do you think we could go about doing this? Remember, we always, what do we have to do first? We always go left to right first. One of those. Because we have to go on the X direction. You follow me? You could sketch it out quick. This is just to give you a visual representation of what's going on. But you don't have to draw it. This is just to help you answer the question. So you can always look back at one of these pictures to see. But once you catch what's happening, essentially that's what it is. So just pretend this graph wasn't here. If I tell you O to A would have just been 8, 6. You see, because OA is a position vector. It's coming from the origin. So I know from that it's 8, 6. Does that make sense? Good. Yeah. Nice. Now, A to O. A to O is the opposite of 8, 6. Alright? So, let's just try to see how that works. So we're going from A to O. We're always moving from left to right first. And then we could go up and down. So we go like this now. So 1, 2, 3, 4, 5, 6, 7, 8. So I went left. So if I went to the left direction, what does that mean? Negative. Okay? So up and right is positive. Down and left, negative. Okay? So let's try from this go down. So we have to go 1, 2, 3, 4, 5, 6. So if I went down 6, I should write for y what? Negative 6. Does that make sense? Okay, good. Now, just to recap that, O to A, we went 6 to the right, which is positive. And then we go 8 to the right, sorry, positive. And then 6 up, which is also positive. So that's how we got 8, 6. Now, A to O, we did the opposite. We went 8 to the left. Then we went 6 down. So that's why we got negative 8, negative 6. Now I want someone to tell me, what do you notice between OA and AO? What do you notice between the two? They're opposite of each other, right? Inverted in the sense of OA is 8, 6 and AO is negative 8, negative 6. So if I already know what OA is, I don't need to work so hard. All I need to do is what? Change the signs. So changing AO instead of saying OA is 8, 6, I could say, oh, AO is just the opposite of that, negative 8, negative 6. Does that make sense? Good. Lovely. Now, B to C. B to C. I'll show you two ways to do BC, especially when we don't have diagrams to help us. Okay? B to C. Now, based on B to C, what we have to do is, if we have a diagram, we go like this. B to C. So I go 1, 2, 3, 4, 5, 6, 7, 8. So I went 8 to the right. So that means BC is equal to 8. And then what do I have to do next? Go up to C. So then we go 1, 2, 3, 4, 5, 6. So we went up how much? 6. So 8, 6. So BC is 8, 6. Does that make sense? Good. Now let me show you how we would have calculated this if we didn't have any of these diagrams here. Okay? But we'll do it with a little exercise now. So if I looked at OA and I didn't have this, oh, you can't hear me? So you can hear me now though, right? Okay, so with this part now, right? We have this BC as 8, 6, right? But what if I told you we had OA first? So O to A is 8, 6. If we didn't have that, we would have known that since it's the origin, we have OA. Once everything comes from the origin is the coordinate. So this would be 8, 6. What do you think the next one would be? OB, right? What do you think OB would be? If we had a guess what OB is. What do you think OB would be? So negative 10 and then 1 at the bottom. Okay? Alright. So we have OB negative 10, 1 at the bottom. What do you think we would get for C? So OC would be negative 2 at the top and 7 at the bottom. Does that make sense to everyone? Good. Go ahead. Tell me. Now you're talking. Now you're talking. So we have OB, we have OA, and we have OC, right? Now, think of it as you driving, right? If I'm starting at B and I want to get to C, these are locations. So think of these as locations, right? So O represents somewhere, A represents somewhere, O represents somewhere, B represents somewhere, O represents somewhere, C represents somewhere. So how do you think I can get from B to C if I was driving? But how would you get from there? We're thinking deep. We're thinking a little too deep. So what's common between OB and OC? Okay, ignore the numbers for now. Think of the letters. We have OB. I'll write it for you to see. OB, OC. What do you notice about those two? They have a common point. Okay? So I want y'all to visualize Anguilla right now. Okay? If you're leaving, say, the high school, all right? You leaving the high school. You want to get to Blowing Point. At some point, everybody must pass that stoplight in George Hill, right? You must pass that. There's no other way around it. Well, there's another way, but if you was to take the main road, you must pass that stoplight at some point. Okay? Likewise, if I'm looking at OB and OC, both of them share one point, which is what? O. So if I want to get from B to C, I just need to go B to O, and then where? O to C. Now the question is, how is that relevant? Now, how is that relevant is if I do not have a graph to help me, that's what I have to use. I have to go B to O. I have to think of it as B to O plus O to C. Yes. So it's like, so if you're going from B to O, then from O, you could get from O to C. Does that make sense? Think of O as a roundabout. So if this was a roundabout and you want to get to C, you go B, go down to O, and then go to C. Okay, y'all following me there? So let's clear this again and go through it again, right? So we want to go from B to C, but we don't have this graph here. Okay, we know what OA is. What's OA? 8, 6. What is OB? Negative 10, 1. What is OC? Negative 2, 7. Now, I want to figure out what BC is. How can I get from B to C? B to O plus O to C. Okay? Now, who could tell me what BO is? Positive 10, negative 1. Can you explain to me how you got that? Because I don't know how you got that. The reverse of what? So OB. Why did you use the reverse of OB? Opposite in direction, right? Everybody understand how I got BO and how he got BO? Good. Now we're going to add BO to what? OC. Now what is OC? Negative 2, 7. Okay? So negative 2, 7. I know I went down with that 7 there just now, but negative 2, 7. Okay? Now if I add these together, what's 10 plus negative 2? 8. If I add negative 1 plus 7, what am I going to get? We got pretend that one didn't happen. So BC is 8, 6. Does that make sense? But we also, if we have a graph, okay? If we have a graph, we don't have to walk it out this way. This is if we don't have a graph. Because if we have a graph, we could sit down here and go what? 1, 2, 3, 4, 5, 6, 7, 8, right? And then how much up? 1, 2, 3, 4, 5, 6. Does that make sense? So just to recap, what was OA? OA was equal to what? 8, 6. Good. Now, what was AO? What's AO? AO. Good. What is BC? 8, 6. Good. Now, a little test here now. How do you think we could get AB if we had to get AB? You do what? I want to get from A to B. What to do? Yep. So A to O plus O to B. Because the common point we have based on the values we have is O. All right? Yes. Yeah. Because once I give you A, you already know that O to A, you don't know what OA is. Because A in itself is just here, right? It's a coordinate, 8, 6. So that means from an origin point of view, OA just is 8, 6. You follow me? The coordinate of C is what? What's the coordinate of C? Negative 2, 7. So therefore, that means naturally OC is negative 2, 7. Because it's the origin. Right? It's just there. It's just a point, you know, in a sense, yes. Does that make sense? Yeah? Okay, now, without even doing any comparisons or calculations, right, I want y'all to tell me 2 geometric relationships between OA and BC. Oh my gosh, y'all make this look too easy. I was trying to, you know, make y'all think a little more, but right, that's correct, yes. OA is the same size as BC, as you can see. And based on the numbers, can you see the numbers? OA is 8, 6, and BC is also what? 8, 6. Great. So because they both have the same vector 8, 6, 8, 6, we know that they are parallel in this case because they don't share a common point, yeah? So same size and parallel. Now, let's calculate the magnitude of OA. So OA. So if we are going to calculate the magnitude of OA, we know that going this way is how much? 8. And going up is what? 6. So what kind of triangle this looks like? And what theory we're going to use? Good. So C squared, or in this case, I should say OA. So OA, the magnitude of OA, or the size of OA, would be equal to 10. Alright, so I want y'all to take this down, take down the answers, and we'll try the next one again. Notice these brackets here, these straight brackets. This indicates magnitude. Alright, so take that down, all these questions and the answers, so you can have as an example. If we wanted A to B, we'd go AOAB. AOOB, sorry. And what if we wanted AC? How can we get from A to C? A to O, then O to C. What if I wanted to do CA? But also remember that CA and AC would be what to each other? They would be opposite, right? So O to A and A to O, we expect them to be opposite. B to O and O to B, we expect those to be opposite as well. So what we're doing here, we're trying to make sense out of this topic connecting the vectors aspect of it. What is a position vector? Position vector is coming from the origin to some point. Then we want to figure out, okay, how can we write this as a column vector? That's when we write it vertically. Now, how do we calculate another vector if we only have one or another point? We just use the origin or whatever common point they have. So if I give you vectors and tell you, oh, this is a vectors, you just look for the common points and make the connections. It's just like driving. That don't mean you never driven before. So you never been in a car. That's fine. You just in a car. That's okay. All right, you guys got it done now? Should have it done by now. All right, so let's try this one here now. I'll give you guys a chance to try it. Then we'll go together. And I'll also show you how we actually work out question 4, the calculation part of it. It's very simple, but you'll see when we get there. So I want you guys to try this question and see what you guys come up with. So I'll give you 10 minutes to do this. 10 minutes.
15.
All right, 15 minutes. All right, you should have it by now. So with this situation here now, we have OF. So based on these coordinates, we could say OF is 8, -6. Everyone got that? So we go 8 to the right and then 6 down. So we go 8 to the right, 6 down. So that's how we got this one here. Now the next one, F to O. So because it's opposite in direction, it's going to turn to what? 8, -8, then what?
6.
Yes. Because this was 8, -6. So therefore, this has to be -8, +6. Okay? So it's opposite stuff we're looking at here. So we go 1, 2, 3, 4, 5, 6, 7, 8. That's to the left. So that's negative and up +6, right? Now GH. Now let's just pretend we did not know GH was here. How could we work this out? G to H. Excellent. So GH would be equal to G to O plus O to H. So G to O is what? -2, -6, right? And I know that because OG, what is OG? 2, 6. Okay? Does that make sense?
Yeah.
And then we're going to add this to OH. What is OH? 6. Nice. 6, 3. So then we have here 6 and here 3. Okay? So then we could add those together. So -2 plus 6 would give us +4. So then we would have that is equal to 4. And then -6 plus 3 would give us what? -3. So we know. Good. So we know that GH is 4, -3. All right.
Teacher.
Tell me. Yes, I see what you trying to do. You trying to do that from the point of view of OH minus G, right?
Yeah.
Yeah. So essentially, it's the same concept. Yeah. But the reason why we try to think of it as adding is to just be mindful of direction at all times, because when you start to subtract, you start to ask yourself, when do I subtract? When do I not subtract? When do I add? So you start to create all kind of factors that kind of could throw you off a bit. You understand what I'm saying? Because there are instances where you have to be mindful of your signs, because if you change direction, it changes to a sign. So you don't want to be questioning whether you got subtracted or added, all that kind of stuff. So just to keep things simple, literally think of it as directions. If I'm going from G to H, all I need to know is G to O plus O to H. You see what I'm saying?
Yeah.
Yeah. But what you said, yes, it could work in that instance. So, next part now. 2 geometric relationships between GH and OF. So, off the bat, What is it? Excellent. So they're both parallel, and OF is twice the size of GH. So let's try to put it into this context now, because let's pretend we don't have our table here. This table here is kind of like having training wheels, right? So we have 4 here minus 3, okay? And we're comparing it to what? OF. And what is OF? OF is 8, negative 6, right? What do you notice when you look at this? Right, so that's like having a 2 outside here. Excellent. So that's like having a 2 outside here, then a 4 here, and a negative 3. What does this 2 represent? This is a scalar multiplier, okay? So in essence, what we're saying is like OF and GH the same thing from this point of view, meaning 4 minus 3, 4 minus 3, is just that OF is what? Double that. So it's like 2 times 4 and then 2 times negative 3, as was just said. So in that case, I would write this and have the scalar multiplier is what? 2, okay? So then I could say OF is equal to 2 times GH. So what I'm saying is OF is what? Twice the size of GH. Does that make sense? Right. Now the question is, what makes them parallel? If we did not have a picture, we would know that they're parallel because of this here, this portion here. You see how both of them have 4, negative 3 to some extent? That's how we know that they are parallel. So they're like scalar multiples of each other, right? So give me another situation with these two, right? What could have been another vector that's parallel to these two? So 4, negative 3. One could be 8, negative 6. Give me a next one. 16, negative 12. Yes. Okay. So once they are scalar multiples of each other, that's what we're going to have. So this here is the answer for that. There's twice the size. That's the size aspect of the relationship. And the next relationship is that they are parallel. So I'm not explaining why yet, because they just told us to state. But later on, we're going to actually go through the explanation part of it, so we understand why it is the case because of these. 4, negative 3, 4, negative 3, we could see that they are both scalar multiples of each other. Once you could see that they're multiples of each other, it has to be both numbers, okay? And it can't be switching signs. It has to be the same thing. Up here is positive, down here is negative. Up here is positive, down here is negative. Same thing. We know that they are parallel. All right? Now the last part, calculate the magnitude of GH. So we want to calculate the magnitude. Yeah, decimal? See.
Something wrong.
Let's see. So in order to do this, it's the same concept as if we were doing what? Pythagoras theorem. Okay? So if you look at it, what do we have here? We have x represents what? 4 squared. And then the y would represent what?
Negative 3
squared.
Good. Now this is why I think somebody probably got something wrong. Because remember, once we square in a negative, it turns to what? So 4 squared is 16 plus negative 9, negative 3 squared is positive 9. Okay? What's 16 plus 9?
27.
27, you sure? 25. 25.
We're not gonna talk about it.
Okay, so therefore the magnitude of GH, guys, would give us 5. Okay? But notice these brackets here and put on the straight brackets. These tell us that we're trying to find the magnitude. So sometimes they could drop a question and just put straight brackets GH. And people would be like, huh? What I even mean by? I never see that in my life. But all I was asking you for is the magnitude of that vector. So don't leave those straight brackets fool you. So everybody got this now, other than the little mistakes that we got. You guys catch that concept just now based on this one, right? When it is, you start to realize you get better. You're gonna get better at it. All right, so let's try this one now. Let's see what's happening here. It's gonna happen with this one, but let's see how y'all gonna calculate this and what you're gonna get. Okay, so I have a question. If I was to find the magnitude of a vector and my answer was 1, what do I call that vector? A unit vector. All right, so we should have this one now. So let's go with the first one. So the first one, what should the answer be for that one? 0, 3. Nice. Remember when we write in vectors, we write them like this as well too. So this is 0, 3. Okay, so OZ, what should OZ be? 0, 9. Now, if you looked at it from a visual point of view, we did not move left, neither did we move right. We just went straight up. So because we didn't move left or right, that's why we got 0. Then we moved up. So let's see who thinking for this now. Z, 0. Who? Nice. 0, -9. Okay, so this question was intentional just to see if anybody would swap the numbers. Yeah? So 0, -9. Good. Now, what are the geometric relationships between the two, OY and OZ? They're collinear, right? And triple the size. So the thing that we had to make sure first is the size we checked first. So OY, when I compare OY, which is this, 0, 3 and 0, 9, I realize, that's 3 times the size. So therefore, I could say OZ is essentially 3 times the size of OY. Okay? And also, when I compare them, right, so they are scalar multiples of each other. So O to Z, 0, 9, O to Y, 0, 3. So if I was to write that out how we do it, so this is our first comment. This refers to size. This is the size aspect of it. So OY is equal to 0, 3, and OZ is equal to 0, 9, but we say that's 3 times the size, right? So that's like having a 3 outside and what? 0, 3, right? So this part here I know is the same. So because this is the same, I know, okay, this is just a scalar multiple of this. But the good thing is they share what? Common point O, right? Which is this. So we can say they are collinear, right? Does that make sense? So one, 3 times the size of the next, and the other one, they're collinear. So that's our 2 geometric relationships. Make sense? And what would the magnitude be? Y'all should have gotten 3 for that one, right? Right. So then that'd be 0 plus 9. Once you find the square root of that, we're going to get 3. And don't forget our straight brackets. Make sense? Y'all understand that, right? All right, good. We're getting better at it. Okay, so looking at this here now, we're going to go through the actual calculation part of it and showing how we can prove mathematically through calculations that they are actually have a relationship that's either collinear or parallel. Okay, so I'm going to show y'all how we justify the reason why. Okay, so looking at this one, before we even start, I want you to tell me, do we have any geometric relationships between these? So double the size and parallel. Tell me why. Javi, come on, tell me. Ladies and gentlemen, do not forget that. Do not forget that. Remember, it's easy to mix up parallel and collinear. We have to look for that last part. The last part is, do they share points? We do not want to forget that, okay? Do they share a common point? So let's go through the way we would go about calculating this. Now, this is a little trick that I use to try and justify whether they are collinear or not, right? So I kind of compare them like this. So I have the OA. Okay, so this is something I'll definitely want y'all to write down. So I have OA here, which is like having 10, 14, and then I have OK. Now the thing is, what I try to do, I try to bring the biggest number on this side and then this one here. No matter how you do it, you'll get kind of like arrive at the same thing, okay? So my little trick to determine this is looking at it this way. So I go like this. So 10 divided by 5 gives me what? 2. 14 divided by 7 gives me what? 2. So both of these numbers gave me 2. So what that's telling me is that I multiplied this 5 by 2 to get 10. And I also multiplied this 7 by the same 2 to get 14. Okay? So these here show that the scalar multiple is what? The scalar multiplier is 2. Okay? So when I'm looking at this, because I know that both of them is 2, that means that OA is twice the size of OK. Okay, so that's my first geometric relationship, right? Now my second, I would say that they are what? Collinear. They are, so this is something you have to write, they are scalar multiples of each other, right? That's the most important part. You have to be a scalar multiple before you could be parallel or collinear. If you're not a scalar multiple, you can't be either one of them, okay? So they are scalar multiples of each other and what? Share a common point, which is O, right? So in this case, I know that they're collinear because they are scalar multiples of each other and share a common point O. All right, so that's OA and OK. So I want y'all to write on this question and my logic for working it out. But remember, you have to look out for this as well. Not only do they have to be scalar multiples, we must look to see if they share a common point or not. If they do not share a common point, we would have said they are what? Well, excellent. So write this down and the answer. What's another way of saying that OA is twice the size of OK? What could I have said instead? I'm saying that OA is twice the size of OK. What else could I say? OK equals half of OA. But sometimes people say, oh, you twice that person's size. Or the next way they would say is, oh, you have that person's size, you know, referring to the other person. All right, so let me go through a next one. I want y'all to assess this the way I showed you just now. Assess this the way I showed you just now, and in 5 minutes, we are going to see if there are any geometric relationships between OA. All right, so let's see what we got here now. So, are there any geometric relationships? That yes was like, I ain't too sure, you know. So we saying it confidently? I heard a confident yes earlier. So let's check OA and MS, right? And OA. So we have 15, 21. And then here we have 10, 14. So I'm getting that from this here. 15, 21. Bam, bam. 10, 14. So 15 divided by 10 is 1.5. And 1 divided by 14 is also 1.5. So these two numbers here are the same. They don't have different signs. They are the same number, 1.5, 1.5. So therefore, I know that MS is equal to 1.5 times the size of OA. That's my first geometric relationship. That's fine. Once both of these here match up, we in business. Yeah? So then the next one, I just determined that they are scalar multiples, right? Based off of this. So if they are scalar multiples, they could either be parallel or collinear. Now the question, what would make them collinear? Right, so if they share a common point. Do these share a common point? So they are what? Parallel. So for this, we could say that they are parallel because OA and MS are scalar multiples of each other but do not share a common point. So notice, just how we divide this, both of them have to be the same sign as well too. So this one can be negative and this one positive. Both of them have to be the same exact sign. Okay? So I want y'all to take this down if you didn't have it. And then we'll check our next question. So basically, y'all would here be here catching the concept as to what is going on here. All right, so you should have this down. All right, let's see what we're gonna do with this. The only time this is not gonna be useful is if you have like 0 and 0, the same zeros, because 0 divided by 0 is gonna give you an error. But based on our earlier question we did, we know that that wouldn't really stop us from realizing that they are parallel. All right, so are there any relationships between these? What does that mean? Okay, but in order to be collinear, we must have what? They must be what for? Scalar multiples. Are these two scalar multiples? No. So can they be collinear? Mm. That's why we check first, right? Just to make sure. Just to make sure, people. So we have 15 here, 18 here. We have -5 here, 9 here. So if we divide, I'm going to get what? -3. And over here, I'm going to get +2. See my problem here? These are not the same. So, yes, I could go and walk the calculator and get this size and that size using Pythagoras theorem and compare it based on size. But, hey, if I'm looking at this, they are not collinear, neither are they parallel, okay? They're clearly not scalar multiples of each other. Does that make sense? Well, in this case, you would see that they're going in an opposite direction, but not necessarily perfectly in an opposite direction. Okay? Because if we had to try to sketch this, when we say they go in opposite directions, we're coming from O. This is O here. This says 15, 18. So let's imagine here was 15 and here was 18. So you may ask, how I know it? How I know to draw it like this? Because it's going from O. That's the origin. So this here is 15, 18. So I know that here to here is what? What point should be G? Now for A, it's going to be, let me make this better. For A, it's going to be a -5 here. And then say a 9 probably somewhere here, right? So from here to here now, this is what letter? What letter would go here? A. So notice how the direction is. So this going that direction, this one going this direction. However, it's not completely in an opposite direction in the sense of the same kind of vector, but opposite, right? They're going, one going right, one going left, but they're going at different trajectories. So this one here now, let's see if you could prove that these are collinear. So in essence, this is another way of asking to show the relationship. But instead of asking you what the relationship is, it's telling you what it is, and you have to basically justify why it is that way. It requires the same process. Let's see how y'all would go about doing it. So write this question down and let's see your justification. All right, so this one, you guys would know that these would be the same magnitude, right? Because once you square the -12, you're going to get the same thing as if you square the 12, right? Does that make sense?
Yes.
And the 5, same thing with the 5s as well, okay? So basically what we were doing with the opposite, the inverse, y'all already know about the inverse. We call those the inverse once we change the direction, right? So the different direction, but we have the same equal size, magnitude, we could say they are inverse vectors, okay? So just take that down for your theoretical. You got it? You guys take this down? Y'all got it, right? Essentially, this here would be like a similar thing. So I want y'all to try this one here, okay? Let's see what y'all gonna get for this one here. These ones don't have relationships, but it's using the principle that we use with AO, BO, and all that kind of stuff. So let's see what y'all come up with for this. All right, so what do we get for OA? What did we get for OA? -5, 6. What about OB? 6, 3. What about AO? 5, negative 6. What about BO? 6, negative 3. What about AB? Okay. All right, so you guys do that one. Go ahead.